Nearest neighbor search, also known as proximity search, similarity search or closest point search, is an optimization problem for finding closest points. Closeness is typically expressed in terms of a dissimilarity function. The less similar are the objects, the larger are the function values. Formally, the nearest neighbor search problem is defined as follows. Given a set S of points in a space M and a query point QAAM, find the closest point in S to Q. Donald Knuth in Volume 3 of The Art of Computer Programming called it the post office problem, referring to an application of assigning to a residence the nearest post office. A direct generalization of this problem is a KNN search, where we need to find the k closest points. Most commonly M is a metric space and dissimilarity is expressed as a distance metric, which is symmetric and satisfies the triangle inequality. Even more common, M is taken to be the d-dimensional vector space where dissimilarity is measured using the Euclidean distance, Manhattan distance or other distance metric. However, the dissimilarity function can be arbitrary. One example are asymmetric Bregman divergences, for which the triangle inequality does not hold. Applications. The nearest neighbor search problem arises in numerous fields of application, including pattern recognition, in particular for optical character recognition, statistical classification CK nearest neighbor algorithm, computer vision, computational geometry, see closest pair of points problem, databases, for example content-based image retrieval, coding theory, see maximum likelihood decoding, data compression, CMPEG2 standard, recommendation systems, for example see collaborative filtering, internet marketing, see contextual advertising and behavioral targeting, DNA sequencing, spell checking, suggesting correct spelling, plagiarism detection, contact searching algorithms in FEA, similarity scores for predicting career paths of professional athletes. Cluster analysis, assignment of a set of observations into subsets so that observations in the same cluster are similar in some sense, usually based on Euclidean distance, chemical similarity, sampling-based motion planning, methods. Various solutions to the NNS problem have been proposed. The quality and usefulness of the algorithms are determined by the time complexity of queries as well as the space complexity of any search data structures that must be maintained. The informal observation usually referred to as the curse of dimensionality states that there is no general-purpose exact solution for NNS in high-dimensional Euclidean space using polynomial preprocessing and polylogarithmic search time. Linear search. The simplest solution to the NNS problem is to compute the distance from the query point to every other point in the database, keeping track of the best so far. This algorithm, sometimes referred to as the naive approach, has a running time of O(n)d), where n is the cardinality of S and d is the dimensionality of M. There are no search data structures to maintain, so linear search has no space complexity beyond the storage of the database. Naive search can, on average, outperform space partitioning approaches on higher dimensional spaces. Space partitioning, since the 1970s, branch and bound methodology has been applied to the problem. In the case of Euclidean space this approach is known as spatial index or spatial access methods. Several space partitioning methods have been developed for solving the NNS problem. Perhaps the simplest is the KD tree, which iteratively bisects the search space into two regions containing half of the points of the parent region. Queries are performed via traversal of the tree from the root to a leaf by evaluating the query point at each split. Depending on the distance specified in the query, neighboring branches that might contain hits may also need to be evaluated. For constant dimension query time, average complexity is O, log n. In the case of randomly distributed points, worst-case complexity analyses have been performed. Alternatively, the tree data structure was designed to support nearest neighbor search in dynamic context, as it has efficient algorithms for insertions and deletions such as the tree. Trees can yield nearest neighbors not only for Euclidean distance, but can also be used with other distances. In case of general metric space, branch and bound approach is known under the name of metric trees. Particular examples include VP tree and BK tree. using a set of points taken from a three-dimensional space and put into a BSP tree, and given a query point taken from the same space. A possible solution to the problem of finding the nearest point cloud point to the query point is given in the following description of an algorithm. The idea is, for each branching of the tree, guess that the closest point in the cloud resides in the half-space containing the query point. This may not be the case, but it is a good heuristic. After having recursively gone through all the trouble of solving the problem for the guessed half-space, now compare the distance returned by this result with the shortest distance from the query point to the partitioning plane. This latter distance is that between the query point and the closest possible point that could exist in the half-space not searched. If this distance is greater than that returned in the earlier result, then clearly there is no need to search the other half-space. If there is such a need, then you must go through the trouble of solving the problem for the other half-space, and then compare its result to the former result, and then return the proper result. The performance of this algorithm is nearer to logarithmic time than linear time when the query point is near the cloud, because as the distance between the query point and the closest point cloud point near zero, the algorithm needs only perform a lookup using the query point as a key to get the correct result. Locality-sensitive hashing. Locality-sensitive hashing is a technique for grouping points in space into buckets based on some distance metric operating on the points. Points that are close to each other under the chosen metric are mapped to the same bucket with high probability. Nearest neighbor search in spaces with small intrinsic dimension. The cover tree has a theoretical bound that is based on the data set's doubling constant. The bound on search time is O, C12 a log n, where C is the expansion constant of the data set. Vector approximation files. In high-dimensional spaces, tree indexing structures become useless because an increasing percentage of the nodes need to be examined anyway. To speed up linear search, a compressed version of the feature vectors stored in RAM is used to pre-filter the data sets in a first run. The final candidates are determined in a second stage using the uncompressed data from the disk for distance calculation. Compression clustering-based search. The VA file approach is a special case of a compression-based search, where each feature component is compressed uniformly and independently. The optimal compression technique in multidimensional spaces is vector quantization, implemented through clustering. The database is clustered and the most promising clusters are retrieved. Huge gains over VA file, tree-based indexes and sequential scan have been observed. Also note the parallels between clustering and LSH. Greedy walks. One possible way to solve NNS is to construct graph, where every point is uniquely associated with vertex. The search of the point in the set S closest to the query Q takes the form of the search of vertex in the graph. One of the basic vertex search algorithms in graphs with metric objects is the greedy search algorithm. It starts from the random vertex. The algorithm computes a distance value from the query Q to each vertex from the neighborhood of the current vertex, and then selects a vertex with the minimal distance value. If the distance value between the query and the selected vertex is smaller than the one between the query and the current element, then the algorithm moves to the selected vertex, and it becomes new current vertex. The algorithm stops when it reaches a local minimum, a vertex whose neighborhood does not contain a vertex that is closer to the query than the vertex itself. This idea was exploited in Voronez's system for the plane, in Raynett's system for the and for the general metric space and metrized small world algorithm, variants. There are numerous variants of the NNS problem and the two most well-known are the k-nearest neighbor search and the I-micron approximate nearest neighbor search. K-nearest neighbor search identifies the top k-nearest neighbors to the query. This technique is commonly used in predictive analytics to estimate or classify a point based on the consensus of its neighbors. K-nearest neighbor graphs are graphs in which every point is connected to its k-nearest neighbors. Approximate nearest neighbor. In some applications it may be acceptable to retrieve a good guess of the nearest neighbor. In those cases, we can use an algorithm which doesn't guarantee to return the actual nearest neighbor in every case, in return for improved speed or memory savings. Often such an algorithm will find the nearest neighbor in a majority of cases, but this depends strongly on the data set being queried. Algorithms that support the approximate nearest neighbor search include locality-sensitive hashing, best-bin first and balanced box decomposition tree-based search. Nearest neighbor distance ratio. Nearest neighbor distance ratio do not apply the threshold on the direct distance from the original point to the challenger neighbor but on a ratio of it depending on the distance to the previous neighbor. It is used in CBIR to retrieve pictures through a query by example using the similarity between local features. More generally it is involved in several matching problems. Fixed radius near neighbors. Fixed radius near neighbors is the problem where one wants to efficiently find all points given an Euclidean space within a given fixed distance from a specified point. The data structure should work on a distance which is fixed, however the query point is arbitrary. All nearest neighbors. For some applications, we may have n data points and wish to know which is the nearest neighbor for every one of those n points. This could of course be achieved by running a nearest neighbor search once for every point, but an improved strategy would be an algorithm that exploits the information redundancy between these n queries to produce a more efficient search. As a simple example, when we find the distance from point x to point y, that also tells us the distance from point y to point x, so the same calculation can be reused in two different queries. Given a fixed dimension, a semi-definite positive norm, and n points in this space, the nearest neighbor of every point can be found in O, now log n, time, and the m nearest neighbors of every point can be found in O, na log n, time. See also. Notes, Caton, Lawrence. Fast nearest neighbor retrieval for Bregman divergences. Proceedings of the 25th International Conference on Machine Learning, 112 Euro 119 Weber, SCHEK, Blot. A quantitative analysis and performance study for similarity search methods in high-dimensional spaces. Andrew Moore. An introductory tutorial on KD trees. Lee, D.T. Wong, CK worst-case analysis for region and partial region searches in multidimensional binary search trees and balanced quad trees. Act Informatica 9, 23 Euro 29 doi. 10.1007/BF00263763 Rusopoulos, N. Kelly, S. Vincent, F.D. Nearest neighbor queries. Proceedings of the 1995 ACM SIGMAD International Conference on Management of Data, SIGMAD 95 PA 71 doi, 10.1145/223,784.223794. ISBN A0897917316. A. Radaraman and J. Ullman. Mining of Massive Datasets, CH3. Weber, Blot. An approximation-based data structure for similarity search. Ramasamy, Rose, ICIP 2007. Adaptive cluster distance bounding for similarity search in image databases. Ramasamy, Rose, TKDE 2001. Adaptive cluster distance bounding for high-dimensional indexing. Olivier, Beaumont. Kermark, Anne-Marie. Markel, Loris. Riviere, Etienne. Voronet, a scalable object network based on Voronoi tessellations. INRIA 5833, 23 Euro 29 doi, 10.1007/BF00263763. Olivier, Beaumont. Kermark, Anne-Marie. Riviere, Etienne. Peer-to-peer multidimensional overlays, approximating complex structures. Principles of Distributed Systems 4878, 315 Euro 328 doi, 10.1007/978-3-540-77096-123. ISBN A978-3-540-77095-4. Malkov, Yuri. Ponomarenko, Alexander. Krylov, Vladimir. Logvinov, Andrei. Approximate nearest neighbor algorithm based on navigable small world graphs. Information Systems 45, 61 Euro 68 doi, 10.1016/JS. 2013.10.006 S. Araya, D. M. Mount, N. S. Netanyahu, R. Silverman and A. Wu, An Optimal Algorithm for Approximate Nearest Neighbor Searching, Journal of the ACM, 45, 6, 891-923, 1998. 1. Clarkson, Kenneth L., Fast Algorithms for the All Nearest Neighbors Problem, 24th IEEE Simp. Foundations of Computer Science PPA 226 Euro 232, doi, 10.1109/SFCS. 1983.16, ISBN A0-8186-0508-1A. Vaidya, P.M. and O., Naaloka N., Algorithm for the All Nearest Neighbors Problem. Discrete and Computational Geometry 4, 101 Euro 115 doi, 10.1007/BF02187718. References, Andrews, L.A. Template for the Nearest Neighbor Problem. C++ Users Journal, Volume 19, No. 11, 40-49, 2001, ISSN, 1075-2838, www.ddjcom1844014449, Araya, S., D. M. Mount, N. S. Netanyahu, R. Silverman, and A. Y. Wu. An Optimal Algorithm for Approximate Nearest Neighbor Searching in Fixed Dimensions. Journal of the ACM, Volume 45, No. 6, ppA 891 Euro 923, Baer, K., Goldstein, J., Ramakrishnan, R., and Shaft, U. 1999. When is Nearest Neighbor Meaningful? In Proceedings of the 7th ICDT, Jerusalem, Israel. Chun-Min Chen and Yibei Ling, a sampling-based estimator for top K-query. ICDE 2002, 617-627, Samet, H. 2006. Foundations of Multidimensional and Metric Data Structures. Morgan Kaufman. ISBN 0-12-369446-9, Zazula, P., Amato, G., Donnell, B., and Batko, M. Similarity Search, The Metric Space Approach. Springer, 2006. ISBN 0-387-29146-6, Further Reading, Shasha, Dennis. High Performance Discovery in Time Series. Berlin, Springer. ISBN A0-387-00857-8. External links, Nearest Neighbors and Similarity Search a website dedicated to educational materials, software, literature, researchers, open problems and events related to NN searching. Maintained by Yuri Lifshitz, Similarity Search Wiki a collection of links, people, ideas, keywords, papers, slides, code and data sets on nearest neighbors, KGRAPH a C++ library for fast approximate nearest neighbor search with user-provided distance metric by Weidong. FLANN a library for performing fast approximate nearest neighbor searches in high-dimensional spaces by Marius Mujar and David G. Lowe. Metric Spaces Library an open-source C-based library for metric space indexing by Karina Figueroa, Gonzalo Navarro, Edgar Carvez. Non-metric space library an open-source C++ library for exact and approximate searching in non-metric and metric spaces. ANN a library for approximate nearest neighbor searching by David M. Mount and Sunil Araya. Product quantization a MATLAB implementation of approximate nearest neighbor search in the compressed domain by Hervé Jegger. MESIF a metric similarity search implementation framework by Michael Batko and David Novak. OBSearch a similarity search engine for Java. Implementation by Arnoldo Muller, developed during Google Summer of Code 2007, KNNLSB a K nearest neighbors linear scan baseline. Implementation by Georges Quay. Copyright not, Neartree a an API for finding nearest neighbors among points and spaces of arbitrary dimensions by Lawrence C. Andrews and Herbert J. Bernstein. NearPy a Python framework for fast approximated nearest neighbor search by L. A. Kraus-Sparman, FDD spatial searching and CGAL the computational geometry algorithms library, PANS a Python library for searching approximate nearest neighbors, optimized for large data set with high dimensional features, developed by Liang Wang.